Hello everyone once again. I want to go ahead and cover airfoils real quickly. This is where we get most of our lift from, so I'm going to kind of cover it and we'll do a quick activity when we return to school. So if you go ahead, if you have a notebook, put it in the table of contents and also put in the top of the next page of notes. If you don't have your notebook with you, you can put on another piece of paper and attach it into your notes later when we return to school. So here we go. Airfoils. Any surface that provides aerodynamic force through interaction with moving air. A good example is if you just stick your hand out the window as you're traveling on the road. I used to do this as a kid growing up all the time to see how my hand would respond to the air flowing around it. So of course you cup your hand and force your hand up, or you can face your hand down and it would force your hand down. It's always a good test to do as a kid, experiment. That's basically how airfoils react for the most part. So there's your airfoils, your hand. Air hits it, deflects. Air goes down, your hand goes up, as we discussed earlier, and what generates lift. So there you go. I would suggest drawing this shape here, airfoil shape in your notebook or on your notes. We're going to label pieces of it here in a second. So remember, an airfoil is just a 2D cross-section of a 3D wing. So if you draw that. So any surface that provides aerodynamic force through interaction with moving air. So we have a direction of flight going to the left. Of course, air is going to the right. As it hits our airfoil, then that generates lift. Leading edge, you can just draw a little arrow, point to that. Point of first contact between airfoil and moving air. Some airfoils have a very defined leading edge. Other ones have a less defined one. It's harder to kind of pinpoint. But pretty much where just the air initially hits that airfoil is the leading edge. And of course, you can pause this video at any time to make notes or label things and then restart later. Trailing edge, very simple to find, very end point, the tip. Point of last contact between upper and lower surface of airflow. Chord line is a imaginary line drawn between the leading edge and the trailing edge. So you want to go ahead and label that and draw it on your drawing. You have camber. Camber is a curve of the upper and lower surface of the airfoil. Some airfoils are symmetric and have the same upper and lower camber. Some do not. Some typically have more curvature on the upper camber and not as much curvature on the lower camber as you see here in this example. You label those two parts. And then determines the airflow velocity on the upper and lower wing surface. And then that dotted line, if you want to draw that, that is the mean camber line, of course, going the mean between the upper and lower cambers. Camber designed into an airfoil to increase the maximum lift coefficient. And then this minimizes the stalling speed of aircraft using the airfoil. We're talking about how on smaller, more personal aircraft or training aircraft, they want to have airfoils to create lots of lift. That way it's easier to fly. And then, of course, as you go faster or don't worry about as much lift, then obviously they're willing to give that up for other reasons, stability, control, maneuverability, things like that. High lift devices, of course, this thing going back to the flaps discussion. If you extend the flaps, that increases the camber equally on both wings. So therefore it increases your lift and increases your camber. There's a line drawn there. You don't need to draw this in your notebook unless you want to. You can make notes about it. And increases the lift and drag at slow speeds for takeoff and landing, as I talked about in the last video. They typically only use flaps for that reason during those two times, takeoff and landing, and then retract them when they're in normal flight. Angle of attack, we briefly mentioned yesterday. Excuse me. Angle between the chord line and the direction of the relative wind. Of course, the steeper the angle, the more lift you generate, because it creates more deflection. But on the other hand, if you go too high of too high of angle of attack, that becomes a stall angle, and then of course you can fall out of the sky, which we don't want to happen. And then, so the maximum angle of attack, where airflow separates from the top wing surface, is a critical angle of attack. Condition is called a stall. See on the left picture, what we want to see, nice airflow over and under our airfoil. As we increase the angle of attack, though, notice we talk about the Coanda effect. We don't want the air to separate from the top of the airfoil. In this picture here, it has separated, and so that's what we get stall from, because at that point, you basically are not creating as much lift as you need. If you go any higher, you could create no lift and then really fall out of the sky. Excuse me. Wing components review. You have relative wind, hitting it, leading edge, upper camber, trailing edge. There's your chord line. That's the solid line. You have your lower camber, angle attack. The dotted line is your mean camber line. So hopefully you have all those pieces labeled on your drawing. And then some different shapes of wings. Top and bottom view of the airfoil shape. On the left one, you have the elliptical shape. So you have that kind of shape right there. You have straight. The little front leading edges or corners are rounded, but everything else is pretty straight on that wing design. You have tapered. So see there's a slight taper in the leading edge, but a really big taper in the trailing edge. You have swept back. So those are swept back wings on this design here. You have delta. That's the Concorde flying. You can tell the cockpit's lowered back when they used to fly. But see that forms a shape like a triangle. So they call that delta wing. Please go ahead and record this equation in your notebook. Talking about aspect ratio. The ratio of wingspan to the average chord width. The higher the aspect ratio, the higher the lift efficiency. So aspect ratio is span divided by average chord width. And so for this aircraft's ratio, our span is 36 feet, and then the average chord is going to be 5 feet. So we divide by that. So when we divide, feet cancel, and our aspect ratio is 7.2. Well, and the platform of this one, anyone want to guess? And that would be tapered. This one, you see a very, very narrow wing, only 2 feet average chord, but a much longer span, 50 feet here. So 50 feet divided by 2 feet, and then our feet cancels. We have an aspect ratio of 25, much higher than we saw over here of 7.2. That's why gliders you tend to see longer wingspans, but also more narrow wingspans, because they have a higher aspect ratio, which then, of course, generates more lift for them. And this platform, you want to guess on this one? And that is tapered. Wing area, total surface area of the wing. Go ahead and write this equation down. Is wing area equals span times average chord width. So this one, we have 36 times 5, and that is 180 square feet. And then this one, we have 50 times 2, and that would be 100 square feet for that wing area. And that's it. But just to recap once again, gliders, like I said, you're going to see more longer wingspans, but much narrower chord. Other aircraft, not necessarily that same design. And we'll talk more about that when we get into our actual balsa gliders. Okay, so we're done with those notes. You can cross the page out, sign the bottom of the line, or sign the line, sign the bottom of the page, witness, sign, date if you have a witness. If not, wait to get to school. I said on the last video that to go ahead and look at, I passed out 1, 2, 2 in case you missed it. So just kind of review this to you. I gave you this packet in class. Please work on this now and get it done as much as you can. If you have any questions, remind me or send me a remind message or email me. That's this packet here. And then I did not pass this other packet out. I meant to, and I left it sit on my table when everyone left. But if you want to look at this one, not that one. Come on. Okay. This one here, I didn't get to pass them out. If you have a printer, you can print it out and work on it. If not, then you can just write the answers in your notebook or somewhere else and then transfer those answers over to the packet when I pass them back out to you whenever we return to school. As for 1, 2, 3, what we just finished here, airfoils, that activity we'll do in class. It's a real quick, simple activity that we can do, that we need to do in person. So we'll do that in class, and that will lead us up to 1, 2, 4 when we return also, and that's going to be our atmosphere. I decided to stop there for right now. We'll say more days of school we're going to miss, but I think we'll stop there for now and like present that in class to you. And then also, yeah, just stay warm, guys, and hopefully we'll see you soon. Thank you very much. I was going to say one more thing. If you haven't already submitted your historical PowerPoint 111, please don't forget to submit that on Power Learning. When we return to school, bring your visual to me so I can mark that on your rubric, and then I will grade those as soon as I can. And that's it. Thank you very much.